screens. Okay, so welcome everyone to the MATH1231 live stream for calculus. Now we're going to be going over the Term 3 2019 exam. Now just a reminder, later at 2 p.m. there'll be an algebra live stream. So this is just going to be Jonathan and myself. Maybe we should put our names on this slide actually. So I'll just put, oh, it's very colorful. So I'm Joshua.
And I'm Jonathan.
Yeah. So just so you know who's talking. So I'm actually going to start off with the first problem and work out how to change the page. All right, so I might just mute your mic, Jonathan. Is it muted? Good. Okay, so we're going to start off with the first problem, which is about an open interval of convergence. Now, if anyone does have any questions, feel free to ask questions by unmuting your microphone, but if you want, you can just click in the chat, send a message in the chat for anything that's confusing you. Now, the open interval of convergence, if you do look in the notes, you will see there is a nice definition for something called the radius of convergence, and you can use that, but that's not how I'm going to approach this problem. So you can use the definition of radius of convergence. But if you read the proof, you'll see that the radius of convergence just comes from applying the ratio test for a power series. So I'm just actually going to start a bit more basic and say, let's apply the ratio test. So first things first, I need some notation. So I'm going to let AK be the expression here. It's going to be n cubed over 3 to the power of n and x minus 1 to the power of n. So I'm told that the color is not very visible.
It's quite visible to me, I think. That's fine, yeah.
I'm not sure how you change. Maybe I'll just go for white. Yep. Actually, this blue does look a little bit dark. Let's go for that.
Yeah, now you're using, yeah, white chalk is always better.
All right, so we have this definition here. So we have AK. Okay, well, immediately I'm making a mistake because one says K, one says N. So let's fix that. AN is this expression here. And I'll just say that's something else. So to apply the ratio test, you need to consider what is happening to the ratio of the next term compared to the previous term, telling you how big the next term is compared to the previous term. And we don't want to worry about negative signs. I'm just worrying about, I want to worry about positive quantities. So I'm going to put absolute values there. And I'm only concerned about what's happening for large values of n. So we're looking at a limit. So I'm trying to consider what is this limit doing. So, well, just put in the expression. We have an n plus 1 cubed over, it's going to be quite hard, 3 to the n plus 1. We have an x minus 1 to the n plus 1. And all of that is being divided by n cubed, a 3 to the power of n, and an x minus 1 to the power of n. So to make any sort of progress, we're going to have to simplify this. So let's just combine all the terms together, which look pretty similar. So first things first, I'm going to take this n plus 1 cubed. I can write it over the n cubed. I'm going to take this 3 to the n. Now this is on the bottom, so when I take the reciprocal it does pop up to the top. So I'm going to get a 3 to the n over a 3 to the n plus 1, and this x to minus 1 to the power of n plus 1 over x minus 1 to the power of n. Now quite nicely powers simplify in this. So the only thing that I really need to do any work with is this polynomial. So a little bit of simplification first. This is, let's see, I'll keep it like this, n plus 1 cubed over n cubed times a 1 over 3 times an x minus 1. So the only thing that's actually changing with respect to n is this first term. Now, it should be fairly clear to you what the limit is for large n. If you look at this, the top looks like n cubed plus some other stuff which is not quite as large. So you should know that the limit of that first expression, that first sort of part of the expression, is going to be 1, but just to make everybody happy, let's just do a little bit of algebra to show that. So I'm going to divide the top and the bottom by n cubed to get, well, actually maybe I'll just combine this all into one expression. So it really is n plus 1 over n, or 1 plus 1 over n cubed. You can verify that is the same, times a 1/3 and times an absolute value of x minus 1. So this limit's fairly easy. It's 1 times 1/3 times x minus 1. So that is just the absolute value of x minus 1 on 3. All right, so this is our lowercase r, our ratio. So what the ratio test says is if this quantity is small enough, if the magnitude of this quantity is less than 1, then we're going to get convergence. And in fact, we're not just going to get convergence, we're going to get absolute convergence. So it'll be an absolutely convergent series. So when that is strictly less than 1. So what does that really mean? Well, it means that x minus 1, well, the absolute value of that is less than 3, or equivalently, x minus 1 is between 3 and minus 3. And that is equivalent to, well, just add 1 to everything to shift these inequalities to get minus 2 less than x less than 4. So the question, I'll just quickly go back up to the top. The question was asking us to find the open interval of convergence. So I should answer as an open interval. So the open interval of convergence is minus 2 up to 4 with round brackets because we are talking about an open interval here. Now for this course you don't need to look at the endpoints, although if you do look at the endpoints here, the behavior is kind of obvious because you'll find that the terms don't actually go to 0. The terms don't get smaller. Do you have any comments about this, Jonathan?
No, that seems fairly straightforward. So you've used the radius of convergence. You could just treat this as a
Actually, I used the ratio test.
Sorry, did you use the ratio test? Ah, okay.
I'm-
Yes, you did use the ratio test. So you've just treated this as a series directly. You said it made a comment at the beginning that you could use the radius of convergence, and then you would have found that to be 3. You would have found the radius of convergence to be 3, and it's centered around 1. So that's 3 minus 1 is the minus 2, and 3 plus 1. Sorry, 1 plus 3 is the 4. Yeah. So there are other methods, as always.
Yeah. So the reason I personally avoid the radius of convergence just is because I always get the definition wrong.
Yes. Yeah.
So, and I know the ratio.
The ratio test is where the radius of convergence comes from anyway. So I'm the same. My brain's too small to hold too many definitions. Okay, maybe we should move on to the second question.
Mm-hmm.
And I think I'll
you need
do
to
that.
share your screen.
Yep. If there's no more. Okay, so going back to the black on white world. In a second. Here it is. Okay, so let me just make that slightly larger. Okay. All right, so now we have what starts out as a very standard question, but it has a little bit of a twist. And although it's algebra this afternoon, there is a bit of algebra in here. I wonder whether the algebra live stream this afternoon will pick up on that. But anyway, I'll do the whole thing. So for the first part is just find the general solution to a differential equation that's given there. It's a second order differential equation with constant coefficients. It's a linear differential equation, and it's inhomogeneous. So you probably need to know what all of those different terms mean. It's second order because there's second derivatives. It's linear because there's a linear combination of y and its derivatives on the left there. And it's inhomogeneous because that's not equal to 0. It's equal to some function of x. Okay, so what I would like to do is just solve this. Okay, so the first step with this inhomogeneous equation is to solve the corresponding homogeneous equation. So let me just get a pen. I think I'll use black. So part A, the first step is to solve. Maybe I'll write that down. First, solve the corresponding homogeneous equation. That means with the right-hand side replaced with 0. And that's the method. Oh, keeps happening to me. The method for solving these things is to, well, it comes from making a guess, but that has sort of been distilled into what seems like a more systematic way. Is we write down what's called the characteristic equation. So I'll say this has characteristic equation, and you get that by, so the second derivatives get replaced with something squared. I'm going to call that something lambda. The first derivatives get replaced with just that something lambda, and the y itself is just a constant in this equation. Okay, so this is a quadratic equation in some parameter, which I'm calling lambda. You might call it m or r or t, or there's all sorts of things. Probably t is a bad idea because t often gets used as the independent variable in the equation. Okay, this is a quadratic. We know how to solve these. So this is, I can actually, this one is being designed so it's easy to factor. But of course, you can always solve a quadratic using the quadratic formula or completing the square. And so we find that lambda equals 2 or 3. And then immediately we can write down the general solution to the homogeneous equation. This is just a step along the way. To the homogeneous equation. This is, I'm going to call it with a little subscript h just to remind me that this is not the solution we want. This is a solution to the equation where I put a 0 on the right-hand side. And it's a linear combination of two solutions e to the 2x and e to the 3x. The 2 and 3 are what the values of the lambda. And a and b are constants. Okay, so that's the solution to the corresponding homogeneous equation. Now, what we want to do is to, the next step in this process is to find just one solution to the original equation. Maybe I might try and put this all together on one. So I'll work over here on the right. Okay, so, okay, so I might just do this. So now we want to find a particular solution. And we usually call that y subscript p, a particular solution. And to do that, we just make a guess. I say try or guess. And it's got to be an educated guess. And because the equation is a whole lot of derivatives added up, come to e to the x, well, what could the original function have been? It's really got to involve something to do with e to the x. Otherwise, you know, you're never going to get an e to the x coming out after you add up combinations of its derivatives. So now this one turns out to be the easiest possible example, because if I were to make the guess yp is some multiple, I'll call alpha, of e to the x, what could go wrong is that the e to the x could be actually also a solution to the homogeneous equation, in which case that's something which will always give you 0 when you plug it into the equation, left-hand side. And then you couldn't possibly get e to the x on the right. But as it happens, e to the x is not part of the homogeneous solution, so this guess is fine. If it had been, the standard trick perhaps is to multiply by x and then try again and see if that is now no longer part of the homogeneous equation solution. Okay, so this one's probably going to work. If we've made this guess, then you know, this is just about the easiest possible example. The first derivative is just the same, and the second derivative was also alpha e to the x. And if this is going to be a solution, then it has to satisfy the equation. So we need yp double dashed minus 5yp dashed plus 6yp. That's got to be e to the x. And so that is alpha e to the x minus, I don't know why this keeps moving. Oh, it's the scroll bar at the bottom. That's annoying. I need a rubber. Okay, 5 alpha e to the x plus 6 alpha e to the x is e to the... I wonder if I can make this full screen. There we go. Sorry. Okay, this should be e to the x. And doesn't take that much work to simplify this. This is actually just, so there's e to the x minus 5 plus 6 is 2 alpha e to the x. And so we conclude that alpha is 2. And in fact, we can go back the other way. This is, if alpha is 2 is exactly what we want. Okay, so the general solution, is the sum of the homogeneous one that we had before and the particular one that we found. That tells us all the possible solutions. Plus, we guessed that it should be alpha e to the x, and we found that alpha was a half, so that's a half e to the x. Okay, so that was part A, and this is a very standard thing. Now we've got something which tests a little bit whether you've gone a bit further in this understanding here. Hang on, sorry. Right, that was a okay. So now what we want to do is for alpha, part B, we want to just write down a basis for the kernel of T and show that e to the x is in the image of T for some linear map. Now, if you look at this linear map, maybe I might just so we, no, I might just do it over here. Okay, this is where I'm going to do B, just so we can see everything. Okay, so alpha says write down a basis for the kernel of T. We don't have to do any calculations here. It's just telling us that we should be able to see immediately what this is and write it down. Now, T of y is the left-hand side of the equation. Okay, and what do we mean by the kernel of T? The kernel of T is all the things you can put into T, all the y's you can put into T that produce 0. And that's exactly what the solution to the homogeneous equation is doing. It's all the things you can plug into the left-hand side that give you 0. So we can immediately write down, maybe I'll just write it as a sentence, a basis for ker T is, now a basis is a set of elements and it's a minimal spanning set. So you should just be able to spot straight away that it's e to the 2x and e to the 3x. And this is a set of two things. Where does the e to the 2x and e to the 3x come from? Well, we said that all of the solutions to the homogeneous equation are a linear combination of e to the 2x and e to the 3x. So that's exactly what we need for a spanning set, and a basis is a minimal spanning set. We need linearly independent. There is no way that you can write e to the 2x as a multiple of e to the 3x, a constant multiple. So these are definitely linearly independent. Okay. All right. So the alpha part there didn't require any explanation because the question just said to write down. Let me just get rid of that red. Okay, now for beta, what are we supposed to do here? Show that e to the x is in the image of T. How do we show that e to the x is in the image of T? Well, what we need to do is find something that you can put into T for y that gives us e to the x. And that is exactly what the particular solution was doing. So let's just check that. So T of a half e to the x is equal to, so this is a half, second derivative, e to the x, minus 5 times this first derivative, which is a half e to the x, plus 6 times a half e to the x. And this should be, if we've done everything right, well, it's got to be e to the x. Okay, so we've shown that there is something in the domain of T that gives us e to the x. So that's all. This is, I guess, complete answer here. So I'll just say, so e to the x is in the image of T, because we've found something that you can put into the argument, put into T, and it gives you back e to the x. Okay. So those last two parts there were really really about whether you understand how you can make these connections between this more, this something that doesn't look like linear algebra, but actually really is some linear algebra, and use the terminology you've learned in the linear algebra half. Any questions about that? Joshua, do you have any comments?
No, but I suppose if you did run into this exam, so someone missed the lambda part, they say, this is how you find lambda?
So right back at the beginning, I guess that's just a standard method, what it was for. Yeah, okay, well, so there's a standard method for finding the solution to a homogeneous second order constant coefficient differential equation. And I'm just following the standard method. I mean, if you want to see how this method comes about, then I guess it's probably maybe read the course notes. It's a little long story, but of course, you know, it's not that long. We just did something a bit like looking for the particular solution. We have y equals e to, we try y equals e to the lambda x, plug it into the equation, and what pops out is that characteristic equation for lambda. But you should you know, have a look at the course notes maybe. So if the right hand side of the dE was e to the 2x, then we would definitely have a different guess. Yes, that's right, different type of guess, because e to the 2x, so this is a question from the chat, if we had e to the 2x on the right hand side of the equation, then that does appear in the solution to the homogeneous equation, and we then need to modify our guess. So we would, in that case, we would try alpha times x times e to the 2x. And why are they linearly independent? Okay, so maybe I'll just actually write down that first one. So maybe just a couple of the questions. So if right hand side was e to the 2x instead, then guess yp is alpha x e to the 2x. Yeah, so that was the first one. And the second question here is why do we know that the exponential, so e to the 2x and e to the 3x are linearly independent? Well, if you've got two things, they're linearly independent if one is not a multiple of the other. But you could even go back to the definition and say, and consider what happens, suppose, if you have mu1 times e to the 2x plus mu2 times e to the 3x equals 0. This is the type of equation you need to analyze to decide whether e to the 2x and e to the 3x are linearly independent. A linear combination of, can you make a linear combination to 0 without the coefficients being 0? And it's pretty quick to check that perhaps you can easily say if x equals 0, then you certainly must have that. And if x equals 1, then you've got this equation. And the only way for that to be satisfied is if mu1 and mu2 are both 0. You can easily check that. So the only possible linear combination of them is the trivial one. Yes, Joshua points out that, so in my answer to the first question there, if first question I've noted here, if you have if x times e to the 2x was also in the homogeneous equation, then you have to go another step further and multiply by x again in your guess. Yeah.
So I did want to make one comment about part B, because it might actually be helpful if I walked into the exam and saw this question and didn't quite understand what it was trying to tell me. I would probably try and work out what the definitions are telling me. So go back to the definition of the kernel and the definition of something in the image. Although mostly for the kernel, I think I'd have to go back just to recognize it really is saying t of y equals 0, and that really was the problem we solved in part A.
Yeah. Yes, certainly. I mean, I guess the question says write down the basis,
Yeah.
the basis for the kernel. So, answer can just be the basis if you know what you're doing. But if it's probably going to be a little bit out of left field, this question, and Josh was right. You should be writing down what you think what the kernel means, and then you would realize that actually it's telling you that y double dash minus 5y dash plus 6y equals 0. And hang on, we've just actually solved that equation. So yeah.
Yeah. So yeah, so write down, because if you know what you're doing, but getting to knowing what you're doing, that might take a step.
Yes.
So we move on to problem, next one.
I think, yep.
There we go. Jonathan's the owner of the notebook, so he'll have to decide. So anyway, I'm going to be doing this question. So this is actually a really quick question. It's give an example of a divergent series, but not just any divergent series. You want to make sure you're given an example where the terms are positive and the terms are actually getting smaller. So this is, well, I like to think of this as a series which is trying to converge, but it's not really going to be able to, because we are looking for a divergent one. So this is a necessary condition, but it's not sufficient. So I do want to know if anyone can give me an example of such a series where the terms do get smaller, but the series itself won't converge. So yeah, that's kind of the answer I think the person who wrote this was looking for. In fact, I know
you
it
wrote
was.
It, didn't you?
Yeah, I was going to say, I know it was because I wrote the question. This is exactly what I would have expected, the harmonic series. So that would be my answer. No, that's too big. So in some sense, it's even a classic example. So the classic example is harmonic series. And just to make sure the person who's reading this knows exactly what series I'm talking about, this is the series summing from n equals 1 up to infinity, 1 over n. So this is the harmonic series, which is in some ways connected to the log function. Now, there are other examples you were taught during the session. Does anyone know another example? Something maybe closely related to the harmonic series? I mean, if I wanted to be cheeky, I could take twice the harmonic series, but I'm thinking of another class of examples. One over a to the n, a, n. Yeah, I think I see what you're saying. So this is actually a p series, which is the other case. In fact, the harmonic series is a special p series. It's a p series for p equals 1. So let's just say some alternatives. You could have some k, oops, say some n equals 1 to infinity, 1 over n to the p, where p is between 0 and 1, a divergent p series. So those are good examples, but the harmonic series, that's what I expected people to remember when they look at this question. So any comments, Jonathan? Will this be on the exam? Well, I don't know. I didn't write it. It was on the exam I wrote for this term, for the term 3, I should say, last year. And I think you should know some of these classic examples. You should know that terms tending to 0, that is a necessary condition, but you should appreciate that it's not sufficient. It's not enough just to have the terms going to 0.
I would say that there is usually a question that's sort of a bit like this in the exam, because there's a question, there's usually questions where you may or may not use the nth term test. And that's one that students often get wrong. The nth term test says that if the terms in the series do not go to 0, then the series can't converge. But for whatever reason, there's often confusion between whether the terms actually converge to 0 or whether the sum of those terms converges. And so this is, I guess this question here is designed to sort of really, get at that kind of idea. The terms in the terms must be going to 0 for the series, the sum that is, to converge. Sorry, for the series to converge. But they've got to be going to 0 fast enough. So whether they go to, if they don't go to 0, certainly doesn't converge. If they do go to 0, that's a good start. But you still don't know it converges. So there is usually something in the exam that is something along the lines of this with the nth term test. Yeah. Okay, maybe we'll move on to the next one. I think it's back to me. Shall I share my screen for the next one? You finished there, Josh?
I am, sorry.
Yeah. Okay. All right. So the next one is actually one that is in the sample test, I think, on Maple TA for the exam. There was a bug in it the first when it was first released, but it should be fixed now, I think. So we have a function from R to R. So this is a real function defined on the whole real line, and it gives real, gives real output. And we're told that the Taylor polynomial of degree 4 around 1, around the point 1, so that's why it's a Taylor polynomial in x minus 1, is shown there. And so it's a quartic in x minus 1. And so we want to show that 1 is a stationary point of f. Now, when students did this exam last term, there was many students just assumed that we were asking for a stationary point of the polynomial. Okay, so the question asks you about a stationary point of the function f, and can you deduce that from its Taylor polynomial? Well, of course, the Taylor polynomial is made up. Well, it's a polynomial, but the way you get the coefficients is with by taking derivatives of f. And you might notice that this Taylor polynomial has got no term with x minus 1 in it. The first power is missing, and the coefficient of the first power is f dashed of 1. Maybe I might just write down the formula for the Taylor polynomial, although you wouldn't need to do this in the exam if you know what's going ahead, if you know what you're doing. So maybe I'll just write that down. So formula for P4 of x is, so it's f. So this is the formula for about 1. So it's f of 1 is the constant term, that's minus 2, then plus f dashed of 1 times x minus 1 plus f double dashed on 2, that's a 2 factorial, or just 2, x minus 1 squared, plus f triple dashed, the third derivative, on 3 factorial, x minus 1 cubed, plus f, well, you could start writing a 4 in brackets here, but that's 4 factorial, x minus 1 to the 4th. That's the fourth degree Taylor polynomial. And now you'll notice that there is no constant term in here, and that's this one. It's sort of missing. It's missing. There's nothing in there. Okay, so f of 1, maybe I'll just use some different colors here. So that one is that one. F dashed of 1 is missing. So this is the quadratic part, and so on. Okay, I've got one more highlighted color. That's good. Oh no, I've got green as well. Okay, I think you get the idea. Okay, so so you can see you can just immediately read off from the Taylor polynomial that the first derivative is 0 at 1. So maybe I'll write that in words. Since there is no x minus 1 term, f dashed of 1 equals 0, and hence 1 is a stationary point of f. It's a stationary point of f, right? It's of course it's also a stationary point of P4, but it's a stationary point of f is what we wanted. Okay, so I'll state the first bit was you wouldn't need to write it down in the exam, but just to understand it, I've written it down. Okay, so part B, is 1 a local maximum, local minimum, or stationary point of inflection? Give reasons. Okay, so you know that there is a second derivative test for stationary points that you probably should have seen at high school. We've extended that to higher orders in MATH1231. But all we need here is just the usual second derivative test, and so that involves looking at the second derivative. So just matching up terms, you can see that looking at the yellow ones, I might just got it. Okay, from the yellow stuff, we can see that f double dashed of 1. Sorry, I've gone and messed this up. No one said anything in the chat. Not even Joshua. Okay, what should they be in there? 1. Okay. F dashed of 1 on 2 is equal to 5. Okay, so so that certainly tells us then that f dash double dashed of 1 is a positive number. And if it's a positive number, if the second derivative is positive, that means that it is a local minimum. So 1 is a local minimum point. Okay. The nice thing about this Taylor series idea is essentially we can see that we can see immediately that it should be a local minimum, because looking at the Taylor polynomial, the first term is a constant, then there's no the 0th term is a constant, there's no first order term, then we've got something quadratic with a positive coefficient, so it's a quadratic with a graph that looks like a smile, and then we've got cubic terms and so on. But when you're very close to the point 1, the cubic terms are much smaller than the quadratic terms, and the quadratic terms dominate. So really, if you're interested to know whether this is a local minimum, maximum, or stationary point, if you've got some quadratic terms, they're the ones that dominate, and whether the coefficient in there is positive or negative tells you whether it's a smile or a frown. And if you had no quadratic terms, then you would go on and look at the higher order terms. But here we had a quadratic term, so it's a local minimum. I think I've run out of things to say on that. Any questions? Will it be okay to take the first and second derivative? Well, what are you going to take the first and second derivative of? So the question is asking about stationary points of f, and so you need to say what is the first and second derivative of f. If you take the first and second derivative of P4, you need some way to justify that that's the same thing as the first and second derivative of f. Well, I mean, you could do that, but you can just read them straight off the. I mean, how do you know that the first and second derivatives of P4 are related to the first and second derivatives of f? That's the formula that tells you how you get.
I would say that if somebody was going to do this, they would have to start the way you started and write down the formula to say, this is the connection. Because if I took your
Yes.
formula, you have your formula there, right? So you have P4.
Yes.
So you said P4 was written in terms of these derivatives. If I took your expression and took derivatives and substituted in 1, that sort of would give me an equation. But by that stage, you should already know the coefficients tell you the answer.
Yes.
So it's kind of a bit of a
I
strange
think
way
I
to do
think
it.
anyone in the exam who just took derivatives of P4 and talked about whether or not they were positive or negative would not have got full marks, because you need to really link it. You need to be saying why this. The question doesn't say what are the does P4 have a stationary point, and what's the nature of that stationary point. It says what's the nature of the stationary point of F, and so you need to and particularly in part B where it says give reasons, and part A says show, and part B says give reasons. So you do need to make the link between P4 and F in some way.
Yeah. So I think it actually would help in the explanation to write down the definition for P4. It's not very long.
Yeah. That's something you should be able to write down quite quickly. It's not something you should is too hard to remember. I think it's something that's all the terms are relatively have the same format, and they're something you definitely should know.
Any questions on that before we move on?
I think we should move on to. Now we're going. This was all of question 1, or all of the algebra in question. Sorry, the calculus in question 1, and the question 1 was common with the higher course, and now we're going to move on to question 3, which was the calculus part of the exam, which was only for MATH1231, not MATH1241. Sorry, 1231, not 1241.
So actually, let's see how this goes. Try a small poll. So we have 2 series here. I'm curious to know whether people think this first series is a convergent series or not. We have 1 vote so far. Maybe that was Jonathan. It takes time to hold it up. So I think people saying it does take time to vote. I think it took longer to type the response than to vote, honestly. Eight people left. Still over 50% have voted, so right. Oh, shoot, I clicked the end. I want to actually show the poll. Well, the response was, there was about 9 saying that it was no and about 15 saying yes, which doesn't actually sum up to 22 participants, so there's something suspect about that. So does anyone want to try to justify their yes or no answer? So I might let you know, I voted no, it doesn't converge. Yeah, so this is another question about the nth term test, which touches on the concept of the nth term test. So for part A, well, you just need to note the following. So these terms, n cubed over n cubed plus 12n squared plus 3, well, that tends to 1 as n tends to infinity. It does not tend to 0. And that's the test, the nth term test. Yeah, so someone's saying it won't converge. Oh, someone wants to use the integral test. I'm not sure I could actually integrate this one myself, but it would be a divergent integral by some sort of integral test. Okay, so that one's fairly easy. What about the next one? Oop. Should be a simple way to crop that. Oh. So what about part B? Does anyone want to give me a quick idea of what they think about part B? So someone says Maple said no. Now we'll remind you that in the final exam, it is just done without any computer assistance. So yeah, that's a good observation. So let's start with this observation. And Maple does say yes, but again, that's definitely not what you want to write in the exam. So we can see that this integral is actually an integral we can do explicitly. And it does link to the original series, but we'll just start with this observation. So this integral is so start with that. How do I want to say this? Well, I'll try and be a little bit explicit. So let's just let f of x be this expression we wrote down. And just note that so the series really is the series sum from n equals 2 to infinity of f of n. So I'm just going to say that by the integral test, the series converges. Now, there's something I'm not quite happy about this, but I might see what Jonathan has to say. So somebody wants to know, can we say that 1 over log x squared converges? So I don't see quite the reasoning there. Do you mean the integral of 1 over log x, the log of x squared converges? Well, unfortunately, that's not a good reason because it doesn't converge, actually. Because the integral of 1 over log x squared, even squared, that's a divergent integral. I mean, if you want to know why, so if I was looking at the integral, if I was looking at the integral 1 over log of x squared dx, well, log goes to 0 quite slowly, so this is going to be bigger than the integral 1 over x for some appropriate range of x, so it just won't work. Yeah, I don't actually know any other way to do this. The integral test is the only way I saw to answer this question. So Jonathan, do you have any comments?
I have to unmute my microphone. That's my first comment.
Okay.
I was talking and no one was ignoring me, but my microphone was muted. So there is something missing from this, I would say.
Yeah.
My OneNote isn't updating with what you've got there, so I was going to paste in something, but it's not. I'll write over everything. So maybe I'll just try. Yeah. I've got. Wonder why it's not updating.
It is updating on the web for me. So is yours syncing?
It should. It was before. Everything else you've written's appeared there. This one hasn't. I don't know why. Okay. Anyway, so if you look at the integral test in the notes, maybe I'll just I'll share my screen. How about that?
Yep.
So, and I've got a screen clipping, I think, of from the notes. So I'll just paste that in. Hang on. Copy and paste. There we go. Okay, so this is the theorem on the integral test, and it says in here, suppose that an is an infinite series with positive terms, and f of x is a positive integrable function on 1 to infinity. So there's a couple of things here. One is, I don't think Joshua noted that the functions involved were all positive, and this is something that you need. Because otherwise, well, if you have negative and positive, you've got things cancelling out on both sides of the the areas and things like that. It's not, you can't just make the same conclusion. Was your integral from 1?
No, my integral was not from 1.
Yeah, does that matter?
No, I don't think so.
Yeah, I think it doesn't actually matter, but the theorem is quoted from 1. So I think we wouldn't take any marks off in the exam for somebody doing the integral test from 2 or 3 or something like that. But strictly speaking, it's worth mentioning that the starting point is, it doesn't matter where the starting point is. Did you have another comment?
Yeah, so my comment was going to be, when I wrote this down, I realized I never thought about the conditions, which is what you mentioned with the positive function,
yes,
the positive terms in the series. So
look at that.
Oh, there we go.
Yeah, so it just arrived. I'll put this down here.
Yeah.
Okay, so yeah, so it's important. Well, I guess a big difference between maybe high school maths and maths in first year is that we actually have theorems, which we really want to be applied, rigorously. We don't just want an argument that says, "Oh, yes, I know that this function does this because of that." You really want to just say the function is continuous and positive, and therefore, by the theorem, such and such happens. So, yeah, I guess that would be the final comment.
So I might actually add that comment to this OneNote file, so when you share it, people see that comment.
Okay, I might just move along to the to the next question. Okay, so was there a question here? Did we miss the power series question? Power series is was there a power series question in the original exam? Maybe I'll have a look at that.
I'll look for it while you're answering this one.
Yeah. Okay. So now we have a This is just straightforward. Do you know the formula sort of question, really? And it's a slight little twist here because well, we've got a surface formed by rotating a parametric curve, and I guess the twists are in the notes. The parametric curve is just described in the xy plane, x in terms of x and y only. Here the description is x, y, and z, but you can see that the curve is actually just in the xy plane because z of t is 0 when we're describing the curve. So this is just the same, but maybe the way it's written is just slightly different, and so you need to be able to deal with that slight difference in the way it's expressed. The other thing is we're rotating about the y-axis. Now the notes does have a remark about the formula for the y-axis, but the formula that's given in the notes is for rotating about the x-axis, and so you need to adapt that formula. So maybe I'll just write down the formula for rotating the curve around the x-axis first, and then say what the y-axis one would be. So to rotate about, sorry, maybe I should say the surface area. The surface area obtained by rotating around the x-axis that would be the integral from, say, a to b. This is the parameter going from a to b, 2 pi y of t times the square root of x dashed of t squared plus y dashed of t squared dt. I prefer to remember this parametric form than the y as a function of x, because if you have y as a function of x, you can obtain this just by saying, well, if y is a function of x, then we'll just set x of t to be t, and then you just get the formula. You'll get the formula for y as a function of x. But we're given in parametric form, so we'll use this one. Now, unfortunately, this is the wrong formula because this is rotating around the x-axis. And I'll just show how you change it. And about the y-axis is, so the only difference is essentially if you're going to rotate about the y-axis instead of the x-axis, you just want to swap x's for y's. And underneath the square root sign, the x's and the y's appear just the same way. X dashed all squared and y dashed all squared. If you switch x and y, you get the same thing. So the only thing that changes is that we get an x of t out the front here. And then we'll just have the same inside. X dashed of t plus y dashed of t. Sorry, x dashed of t all squared plus y dashed of t all squared. Okay, so now we just need to, the question just says we have to write down the formula, but not try and evaluate the integral. So the only thing left to do here now is to just substitute in what x and y are, and to figure out what the range of the t, the range of the, the parameter t. So we have x of t is cos t, and y of t is t cubed. And we want this surface to be for y between 1 and 2. So maybe I'll just have to, that's not too hard. I'll work that out though. For y between 1 and 2, what do we need for t? Well, y equals 1 is telling us we want 1 equals t cubed. So let's take t equals 1, and y equals 2 is telling us that 2 should be t cubed. So we'll take t equals 2 to the 1/3. Okay, and now we just have to write down the formula. So the area is the integral from 1 to the cube root of 2 pi cos x of t is cos t, and the square root, I can do these derivatives in my head, I think. The derivative of cos t is sine t all squared, and the derivative of t cubed is 3t squared. That's squared. Okay, I think that's probably all right just to leave it like that. Maybe you could simplify slightly, but it would be fine just to leave it unsimplified. It's traditional to write the square of sine t like that, and this is 9 t to the fourth. Of course, simplifying, I'm risking actually making a small error in doing that, so maybe it's better not to, but in this case, this is not something that we know how to integrate, so hopefully you've noticed in the question that it says you do not have to evaluate the integral, and then you don't worry about trying to integrate this. But that's the formula there.
Yeah, so the highlight of this question is actually getting the formula for this. And there is a slight, that thing about the x and the y-axis, it's good to make sure you realize what what's going on here. I mean, I'm not sure what the lecturers have told students this term, but I always try and point out the connection here between the volume of the frustum. So, I mean, x here really is playing the role of a radius. And that second part really is kind of playing the role of the arc length. And I think, like Jonathan said, this is the only formula I remember. Every other formula comes from this. Maybe the polar form is worth remembering because it is complicated to get that from this. So.
Yeah, I don't. I don't think we would ask for the polar form in the exam without giving it or leading. Yeah.
At least we wouldn't.
Maybe it's a hint. No, we wouldn't. But it's in another. So if you're watching this in another year, when there's, someone else setting the exam.
Yeah, it's always dangerous to say what isn't. I can say what I would not put in there. I can't say what other people would not. Now, the question the student asked about this power series, that actually is about a power series and a random variable. Did we want to do that one as well?
Oh, no, I think that'll be done in the algebra in the algebra section because that really was an algebra question.
Yeah. So
because that power series was designed for the random variable for the geometric series. Yeah.
I'll make sure I pop into the afternoon stream just to make sure they do it, so no, it doesn't get missed.
Yeah.
Okay. All right. So there's another Taylor series question coming up. Any questions before we move on?
Okay, I think not.
Whoops. So this is another Taylor series question, and in this case, you need to write down the Taylor series polynomial, use that to talk about the Lagrange remainder, and then use the Lagrange remainder to get an upper bound for the approximate error. So Jonathan has already written down the Taylor series, the Taylor polynomial, so I might not do that. I might just get straight into calculating what we need to know. So it asks us for the third degree Taylor polynomial, so I do need to know at least the first 3 derivatives. And for the third part, for the second part, I know I'm going to need the fourth derivative, so I might as well just work them all out now. This is just a little bit of collection work. So we're given this formula. And because of that, we get the following derivatives. So first derivative, this one's fairly easy. Power 3 over 2, 4x, 4 plus x. Now 3 halves is quite nice, because if you lower that by 1, it goes down to just 1 half. Let's get another derivative. So I'm just going to bring this power down. It's just going to become 3 halves times a half. That is 3 quarters. And down by 1 again to minus a half. And I'm going to leave it in this notation just because it looks a bit easier to read. There's not too many derivatives, so I'll keep using this dash notation, the prime notation. Another derivative, minus 3/8, 4 plus x to the minus 3 halves. And I need one more derivative for the next part of the question, so I might as well just do it now, get it all out of the way. So we have the fourth derivative is, well, 2 minus signs become plus 9 over 16, 4 plus x to the minus 5 over 2. So just get a few pieces of information for the series. We know we need to know f0, which is 4, well, it's just actually 4 to the power of 3 over 2. Now, the person who wrote this was trying to be kind because 4 is 2 squared. So you can write this as 2 cubed once you take that power of a half in. So that is just 8. F of 0, that's 3 halves of to the half, square root of 4 being 2. So this is just 3. Second derivative, so 3 quarters of 4 to the minus a half. Well, that's 3 quarters times a half. That's 1 over the square root of 4. So you could be using a calculator for this. You're allowed to use a calculator. Next one, let's see, third derivative, and this is the last one I need to calculate. I need minus 3/8 times 4 to the minus 3 halves. That's minus 3 over 8 times 2 cubed again being 8, so 8 squared. Actually, that's 64. Now, I guess you could leave these as powers of 4, but they're actually fairly nice rational numbers, so I think it makes sense to try and clean these up. All right, so we were just asked, write down the third degree Taylor polynomial about 0. So hence P3 of x. Now, to be honest, I did practice this right before I came to the live stream, and I got it wrong. So I am actually going to write this down because it's very easy to forget parts of this formula, trying to get all these numbers together. So it is supposed to be f of 0 plus the derivative, and I will write this over 1 just to remind myself of what's coming up. It's x minus 0 to the power of 1, so I can just write that as x to the power of 1 x. So if you want, you can write that as x minus 0, but that seems a bit silly. Second derivative at 0 over 2 factorial x squared, and a third derivative at 0 over 3 factorial. Now, we just need to plug these numbers in and we'll have the series. Now, does anyone want to guess what I forgot while I'm doing this? Because one part of this formula is very easy to forget. So f0 was 8, derivative was 3. The second derivative is 3 over 8, but with this 2 factorial. Not the remainder. No, I don't need the remainder here because this is just a polynomial. So 3 over 8 times 2 is 3 over 16. And let's see, just a quick mental calculation. 3 factorial is 6. There is a factor of 3 here, so that's really just 2. So it's, I might write it as plus minus 1 over 128x cubed. So that is the Taylor polynomial. So this question, I think, is really just testing your ability to remember the formula. And it goes out far enough that you need to remember the factorials. And the factorials are what I forgot, actually. When I did this question, I just completely slipped my mind that there were factorials in here. It's not an equal sign. Actually, this is an equal sign. So this is a polynomial. I mean, it is an approximation to the function. So if I wanted to put an approximation in here, what I could say, I mean, the function itself, f of x, should in some sense be approximately this polynomial. But the polynomial itself is just a polynomial. It's exactly equal to this polynomial. Okay, so the second part, the first part is use this, just write down this polynomial. Now the second part was write down the formula for the Lagrange remainder. So this is where the function itself comes in. So you don't need to write this, but just a reminder. Let me get a better color. So f of x would be the third degree polynomial plus what we call in the notes the Lagrange remainder. Now, this notation is actually quite nice because when you look at the remainder, you do see this number turning up quite a lot. So I might write down what the form of the Lagrange remainder is, and then we'll just put it in for our particular case. So the Lagrange form of the remainder, so we usually write it as Rn plus 1. It's going to be the n plus 1th derivative at some point c times x, well, I'll do the general form, x minus the point we're expanding about to the power of n plus 1 divided by n plus 1 factorial. And this is usually why we write it this way. You have the n plus 1 here, that's the number of derivatives, that's the power, and that's the factorial. It's a very nice reminder of all the parts that go into it. So for part B, all I need is this fourth derivative. Oh, and I guess to be fair, I should say C is between A and X. So for part B, the Lagrange form of the remainder, so it's called R4 of X. It is the fourth derivative evaluated at some point C, and C is not completely arbitrary. We do know roughly where it should be. And in this case, it's x to the power of 4 over 4 factorial. Now 4 factorial is 26, no, it's 24, I believe, but just leave it as 4 factorial. I don't think it needs to be cleaned up. And we should say where C is, where the best I can say, because C could be, it depends on what the sign of x is. If x is negative, it's between x and 0. If x is positive, it's between 0 and x. So I just want to say where C is between 0 and x. Just to avoid that slight annoyance about which one really is the smaller number, because x is allowed to be negative. And I think that's actually important for the last part of the question. So let's just all right, and if you have any questions, just drop them in the chat so I can see them. So we have part A, we have the Taylor polynomial, we have the form of the remainder, and now we want to use this to bound the maximum error in using P3 as an approximate. So we're really just asking, what is the largest? I am very silly. I never actually put in the formula for the fourth derivative. So what formula for the fourth derivative? It is, 9 over 16 and a power of minus 5 over 2. All right, so part C, we need to really just take this thing here and work out what we can say about its size. Now, the nice thing here, well, x to the power of 4, that just gets bigger and bigger as you move away from 0. So I understand that very well. The thing that I need to work to understand is what this term here is doing. So it never really hurts to do a rough sketch. This is not really part of the solution. This is me just reminding myself what this looks like. So I have a negative power. This is C, it's 4. And I'm trying to imagine what happens when you look at the quantity 4 plus C, so minus 5 over 2. Well, because of that negative power, it is just dropping. There is, for negative C values, there's problems, but it is just going to be a nice decreasing function. So let me just start by stating that. So because it decreases as C increases, and that's true for C greater than minus 4, for example. C greater than 0 as well, but it is a decreasing function, a decreasing expression. So it just gets smaller as C gets larger. All right, so that means actually the biggest value will happen for the smallest possible value of C. So where can C be? Well, the question says that X is inside this range here. X has to be less than 0.2. So let's say, because we know that first fact, and because we know, well, I know that X is going to be between 0.2 and minus 0.2. So the largest this could possibly be, or yeah, maybe I won't say that. So because of this, what we have is 4 plus C. Well, that has to be less than. So what's the smallest C can be? C is bounded below by minus 0.2 because it's bounded by where X can go. So 3.8. This is going to give me the largest value for that number. Right, and yep, everything else I understand. So I can just put that all together. So thus, well, the magnitude of this remainder is literally just equal to this expression here, And I'm just going to say everything here can be bounded. Well, the biggest 9/16 can be is 9/16 because it's constant. The biggest this second term can be is 3.8 to the power of -5/2. So for any particular x, the biggest that x can be is itself. Well, here it's going to be, Now I'm kind of conflicted. I'm going to say it this way. I'm going to say the biggest for any particular x, this is just this number here. The absolute value of that number there. And over 4 factorial. So that has given me a nice bound. Now this itself can be bounded because I know what x can be, but I think this is what I would put for my answer. It's some expression involving x. So,
yeah, you could. You were wondering whether to put 0.2 in there where x is. Yeah, that would be also nice okay. Bound. Yeah, that would be a constant bound that works for every value of x. So that would be acceptable as well.
I do kind of like this one because it gets smaller as x gets closer to 0. So it sort of gives me a bit more knowledge as x gets closer to 0.
Okay, any questions about that? I think this one is a very practical problem. I mean, these using Taylor polynomials to approximate functions is really what is used in a lot of applications in engineering and other areas. So, and the next one is also similar in that regard. Maybe I'll move on to that, shall I?
Yep, sure.
Okay, so the next question is about bounding an error for a function. Here we're not using a Taylor polynomial of a certain degree, and we've got a function of 2 variables. So for the functions of 2 variables, we stick to essentially the Taylor polynomial of degree 1, although we don't tell you that. We call it the total differential approximation. In second year, you'll look at higher order Taylor polynomials for functions of 2 variables. But here we're just sticking to first order and we're calling it the total differential approximation. Okay, so now there's a couple of complicating issues here. That is, we're not actually given the function capital F, which is the one we're trying to bound and approximate. We're not given that explicitly. We're told that it's related to some other function in a particular way, and we're told information about that function, but we're not told explicitly what it is. We're just told what its value is at 1 and what its derivative is at 1. So hopefully that should be enough information. Okay, so I think what I will do is actually, first of all, include a little bit of theory, because it's something which causes a lot of problems at times. Because there seem to be more than one formula that, what's going on here? There's more than one formula that is sort of somehow associated with these ideas. And in my mind, there's really only one formula, and we're just using it to bound the approximation. So I'll start that way and say the total differential approximation the scroll bar is very annoying. The total differential approximation for F is, okay, so delta F is like a change in F, and that will be approximately equal to the rate of change of F in the X direction times the change in the X direction plus the rate of change of F in the Y direction times the change in the Y direction. So you might read that as this is, so delta f is approximately the partial derivative of f with respect to x times delta x plus the partial derivative of y of f with respect to y times delta y. Okay, now we're interested in an upper bound on the approximate error. The approximate error is really this delta f, and we want an upper bound. And what we tend to do is just look at the magnitude of it. Okay, so this is equal to all of that. The absolute value of it is just equal to the absolute value of it. There's nothing done. Nothing really happened here. But then this is by the triangle inequality less than or equal to. Well, I'll keep it as approximately equal to. If you have the sum of two things, if you have the absolute value of the sum of two things, that's less than or equal to the sum of their absolute values. Okay, so this is called the triangle inequality, and basically it's saying that if the two things you're adding up have the same sign, then then it would actually the first line to the second line would actually be equal. If they have different signs, then the result is a bit smaller. So if you take the absolute value of each of them and add them up, that's going to be bigger than if you added them before taking the absolute value, if their signs were different. Okay, now this also, let's also say this is going to be less than or equal to the absolute value of partial df dx times the maximum possible value of this change in x, or its absolute value. And what we want is to figure out what all these quantities are from the given information. Okay, so this is the formula that we want, and we're told that we're at a point x naught, y naught, which is 5, 2. I'll just say we are at x naught, y naught equals 5, 2, and we are told that the maximum change in x, or uncertainty in x perhaps, is 0.05, and the maximum uncertainty in y is 0.02. Okay, so that's the sort of data from the question. Now we're also told how capital F is related to little f, and that's going to come into our calculations with the derivative. So I might just move over to the right here. So we're told that f, maybe I'll just put a little box around that in red, or maybe I'll highlight it actually. We're told that capital F is related to little f in that way there. It's capital F of xy is little f of x squared minus y cubed. So we want to find out the derivatives of capital F and relate them to the derivative of f, because we're told something about the derivative of f. We're told that it's f dashed of 1 is 2, and hopefully that's going to come out of this. Maybe I'll just make a note of the fact that that x naught squared minus y naught cubed, because that's going to appear, this is what appears in the argument of that function, is at the point we're interested, is 25 minus 3 times 8. Have I got that right? 25 minus 24 is 1. That's nice and simple. So actually at the point x naught, y naught, the combination that's going into the function little f is 1. And we're told information about what the value of f at 1 and its derivative at 1. So that's a good thing. Okay, so now let's use the chain rule to calculate the partial derivative of capital F with respect to x. And so this is d by dx of, and it's f of x squared minus 3y squared. So this is f dashed of x squared minus 3y squared times by the derivative of x squared minus 3y squared, which is 2x. And maybe I will just make a note here and now of what this is actually at the point x naught, y naught. Got to make sure I get my capital F's and little f's distinguished. So that's 5, 2. Oops. And so this is f dashed of, I already worked out that x squared minus 3y squared is 1 when x is 5 and y is 2, times 2 times 5. Okay, I could have probably simplified that. 10 f dashed of 1. Actually, do we know what f dashed of 1 is? We told f dashed of 1 is 2. So this is 2 times 2 times 5. That's 20. Oh, y cubed. Sorry, you're quite right. That hasn't affected me yet. Yes. Actually, I made exactly the same mistake when I did the working before and corrected it, and now made it again. But this hasn't. I did my calculation down the bottom here, x squared minus 3y cubed. So that's right. So that bug hasn't affected me yet. It would affect me in the next one though. So the partial derivative of capital F with respect to y is the partial derivative of f of x squared minus 3y cubed, and that's f dashed of x squared minus 3y cubed. Thanks for pointing that out in the chat. The derivative of 3y minus 3y cubed there is minus 9y squared. And so at the point we're interested in, capital F, at x naught, y naught, partial f dy at 5, 2 is f dashed of 1 again, because that's 25 minus 24, times by minus 9, what's y? Y is 2, y squared is 4. So that's, what's f dashed of 1? That's 2. F dashed of 1 is 2, so this is minus 72. Okay, minus 72. All right, so now we've got pretty much the information we need to finish this off, because what we want is that delta F is approximately less than, I'm just going to use the formula, I'll just highlight the formula. So that's this formula here I'm using. So using this, go back to my regular pen. So we're evaluating this at, let's do this at x naught, y naught equals 5, 2. Maybe I want to move this down a bit. So this is approximately less than the derivative, partial derivative of f with respect to x evaluated at the point we want, which was 20, times by the maximum value of delta x, which is 0.05, and then plus the partial derivative of f with respect to y evaluated at 5, 2, times by the maximum change of y. So maybe I'll just highlight a few things here. So that 20 comes from there, and that 72 comes from there, and I think the 0.05 and 0.02, that's clear where that comes from. Okay, so this now is it's just a matter of working things out. This is 1 plus 1.44, and that's 2.44. So have I answered the question? I'll just read it again. Using the total difference approximation f, estimated approximate upper bound on the error, the absolute error in f of x naught, y naught. Okay, so what we're doing here is we're evaluating some function at a 0.52, but we don't actually really know that that point is exactly at 5.2, and we've the amount that it could be off in the x direction and the y direction are expressed with this maximum delta x and maximum delta y. And this is our estimate of how bad the exact value would be. We haven't actually been asked for what the value is in this question. That would come from calculating capital F of 5.2, which would be little f of 1, which happens to be 3. But it didn't. That 3 didn't actually enter into our estimate of the error bound on the error. So we didn't actually need that piece of information. Does that make sense? Any questions on that? Okay, maybe we'll move on then. Josh, do you have any comments?
No, I don't think so. Just be careful. You have to be careful to use the absolute values. Otherwise, you'll end up with some cancellation, which isn't justified.
Yes. So this question here, you can probably just jump straight to the formula that I've highlighted in green if you know what you're doing. But probably in the exam, experience shows that there's a lot of confusion about which formula should actually be used. So I prefer just to stick with the total differential approximation and work out this other one from it, because if that's what I need. What if you missed f dash to 1? Why would you miss f dash to 1 in the calculation? You mean you didn't read the question, or if it wasn't given? If it wasn't given, then you couldn't get the answer out. Certainly, it's got to be there. There's a question in the first lab test which involves taking partial derivatives like this, and a very popular answer is just to ignore the f and work out the derivative of x squared minus 3y cubed, which is just wrong. I don't know whether that's because students interpret f, the right-hand side there, as f times x squared minus 3y squared, where f is a constant, or just don't know what to do with it and just pretend it, hope it'll go away. But actually that f dash to 1 is probably the most important thing in this question. Well, that's not true. There's two parts to this. One is how you use the total differential approximation, and the other is how you use the chain rules. And there, the f dash to 1 is really the critical thing. Yeah.
I think if we didn't tell you f dash of 1, the most you could conclude is it's less than 1.22 times the absolute value of f dash of 1. I mean, you can work through all the calculations and you do.
Yeah, so f dash to 1 follows through. It's in both terms. Yeah, but yeah.
All right.
Okay.
So one more question. I was going to say there's one more question from the exam, so we'll finish with this one. And lucky me, I get it.
Yes. Leave on a high. The last question is the grand finale, because it's a modelling question, and of course there's many students in this course who are not doing maths just because they love maths and want to become mathematicians. Been told there's quite a few who doing engineering or want to actually use maths in the future, and this is really where you're heading. So hopefully this is your favourite question.
Now,
generally, I'm a bit tongue in cheek there, but
Yeah, the first thing I'm going to say is when you see this question, it looks, well, to me, it looks quite frightening. So I'm just going to say my first advice for this one is just don't panic. Sort of read the question, try and work out which parts you need to answer. And actually, if you look at the first two parts, A and B, they're not really asking for much. They're just asking you to work out a couple of differential equations. So that's half the question there, essentially.
Maybe when we write exams, we should put part A, don't panic.
Okay.
Then part B, write down the ODE.
I'm not sure we can give marks for not panicking, though. I don't know how to test that. Students go into exams with little heart rate monitors, panicking. Anyway, so let's see. So we have a lake. Now, there's a lot of information here, so I'm going to try and highlight the information I think is essential. So it says that there is a chemical spill, which has released 4 tons of a chemical. It's water soluble, so it's going to mix into the water. Now, it does say it was clean water. Now, that's kind of just important because it's saying that there's no other source here. It's just from that 4 tons initially. Now, there was a total of 8 kilometers cubed of water in the lake initially. So again, this is more initial information. And a company has set up a plant to remove and sell the water. Now, the sell part is just there because the water is not coming back. It's being removed. It's going away. Now, let's see. We've defined some notation for you. So VT is the volume of water measured in kilometers cubed. We have PT, which is the mass, the total mass of pollutant measured in tons. And T is the time since the spill measured in months. Now, you'll notice we're not trying to be unkind here. One of the interesting things that can happen with differential equations is the units can change. You might have information given to you in different units, but that is a complication we're avoiding here. We're giving you all the information in the same units. So what do we have? So that's pretty much just setting the notation, setting some initial conditions. Next part is we're told, we're told that there's water flowing in, clean water, so no pollution in this water, flowing in at 0.5 kilometers per month. Again, kilometers cubed per month, that's all nice, consistent units. The water is being removed at this rate, and there is a third source of change, that is the evaporation. So we're told that water is evaporating at this rate here. Again, kilometers cubed per month, no tricky business with the units. Now, the one thing you do need to pay attention to is that evaporation doesn't remove pollution. So it's not going to affect the rate of change of pollution, it just takes away the water. Okay, so let's try and start. So for part A, it just says write down the ordinary differential equation governing the volume of water and also with an initial condition. So you have the rate of change of volume with time. Now you've probably seen in lectures they've said it's the size of the inflow minus the size of the outflow. Now there's only one inflow term here. There's only the river coming in. So the river flows in at 0.5 kilometers cubed per month. And T is measured in month and V is measured in kilometers cubed, so those units are nice. There are actually 2 outflow terms. So there is a 0.2, which is just being removed by the company. And there's also the evaporation, which depends on V itself. So the size of the lake does affect the evaporation. The larger the lake is, the larger the lake is, the more evaporation we're getting. So we can make this look a little bit nicer. So 0.5 minus 0.2 is obviously 0.3, and we get a minus V of t. So that's our differential equation. We need an initial condition. Well, the amount of water was initially 8 kilometers cubed, and T is measuring time since the spill. So we're saying that V of naught, the volume at the initial time, 0 months since the spill, is just 8, saying 8 kilometers cubed. So I don't know if I would necessarily write more there, but I think that is enough for part A. Do you have any comments about that, Jonathan? Your mic is muted, by the way.
I see you did that. No, I think that's good. Yep. I think it's important to also write down inflow minus outflow because it makes it clear that that's what you're doing.
Yeah, it's kind of there's a bit of a balance here. The question itself is quite wordy. I'd like to give a wordy answer, but I'd also like to just give the answer. So I'm trying to balance that here. So for part B, so we're going to be looking at what is the rate of change of pollutant with time? So this does depend on, well, it says here, okay, we're assuming that it's well mixed. So we're going to assume that the pollution is just a nice uniform density over the entire lake. So how is that being removed? So let's see. Now there is no outflow from the lake except for the company and the evaporation. And the evaporation doesn't take the pollutant. Let's see, so rate of change of pollutant with time. Well, that is going to be, just from the company itself, it's going to be the, how would I write this? So maybe words would be better to explain this. So let's say the density of pollutant realizing I can't spell. So the density is the amount of pollutant over the volume, and that's measured in, so how much was pollution measured in tons? That's tons per kilometer cubed. So using this, I can work out how much the company is actually pulling out. So hence, so the company removes the pollutant at a rate of, well, they're taking 0.2 kilometers cubed per month, and I times that by the density. And that's in, well, that is actually, because I've multiplied it out, it's going to be tons. The units on this is tons per month. Now, that's only half of that question, because you also need an initial condition for P, and we are told that initially, the initial spill was 4 tons. So I'm just going to say, initially P naught is equal to 4, which is saying at 0 months, 4 tons of pollutant. Okay, so I didn't actually write down the differential equation though. So I might just slip that in here, how this looks as a differential equation. So i.e. the rate of change of pollution with time is just what the company is pulling out. It's 0.2 P of T over V of T. And we have our initial condition. Now, these are important for the next 2 parts, so let me just highlight them somehow. All right, so for the next part, you need to solve And we're actually given some helpful information. So solve for VT and then solve for PT. So there's a kind of an indication here that you have to do these in a certain order. So for part C, let's just remember what we had. So we had the following equation. And I might just write it that way. So these do depend on T, but it's a little bit easier to read if I don't write that down. Now, does anyone know how we might solve this? You were learning how to model things using first order equations. Does anyone recognize what kind of first order differential equation this is? So I see linear. Anyone else have an idea? I mean, linear is correct, I should say. There is actually another type it falls into as well. So the other type I'm thinking of is separable. So you really have a choice here. You could solve this as a separable equation, a differential equation, or you could solve it as linear. To be honest, I tend to find the linear ones I make less mistakes with. So let's go with the linear technique. Let's find the integrating factor. So to do that, well, I need to rewrite it. So or equivalently, you can rewrite it as dv dt plus v is equal to 0.3. So we have a fairly standard technique for solving these. So there's something known as the integrating factor. Can anyone tell me the integrating factor? Yeah, just e to the t. It's really just coming from whatever coefficient you see in front of here and integrating that. So it is just the integral. I mean, you can just say it's e to the t. Now, you can very quickly get to the answer, but I really like the way the integrating factor works. So I'm going to explicitly write down what's happening. So multiplying by h, we get, or h of t maybe. So you do get e to the t dv dt plus e to the t v is equal to 0.3 e to the t. And the whole magic of this is it is equivalent to the derivative of a product. Or so the magic is this is just the derivative of e to the t times v. That's a very easy problem to solve. If I tell you the derivative of something is this exponential, you know what that must be. So hence, we know that this combination is just going to be, well, the integral here is quite easy. This integrates out to that up to some arbitrary constant. And I'll put back in the t part just to say this is 0.3 plus c. Well, if you divide by the exponential, it's the same as multiplying by the negative power. So that's the general solution. Now we did have an initial condition. The volume started at 8. So let's just use that, using the fact that initially at t equals 0, we get v was equal to 8, what do we get? Well, 8 is equal to 0.3 plus c, so obviously c has to be 7.7 to make up for that, just to balance out that equation. So let me just rewrite this. I'm going to need this for the next part. So we have our v. Now that we solved for v, we can try and solve for p. So let's just recall what we had. So we had dp dt is equal to, now did I get, where's that equation? There is a mistake here. Can anyone spot the mistake? Yeah, it's being removed. It was the inflow of pollution minus the outflow of pollution. This term is the outflow of pollution. So I ignored Jonathan's advice to write down inflow minus outflow, and it did cost me here. Luckily, I knew this should be negative, so I did spot it. So let's fix this up. So it's really the inflow of pollution minus the outflow. Now the river flowing in was clean, so there's no pollution coming in that way. There is only the pollution being removed. So it is important to get a negative sign. Let's go back down here. So it was minus 0.2 the p of t over v of t. Now, if I saw this equation in any other circumstance, I don't think I would be really able to solve it, not explicitly. But here we are given that we know an expression for v of t now, so we know it's minus 0.2 p of t over 0.3 plus 7.7 e to the minus t. So again, we only ask you the sort of questions you should be able to answer. So this is an integral. This is a ODE. You should be able to solve a nice first order ODE. Does anyone know what type it is? I mean, we only teach you about 3 types, I think. You're either learning about exact differential equations, linear differential equations, or separable differential equations. Yeah, it is separable. In fact, I think it's linear again, but separable looks a lot more appealing in this case, to me at least. Do you have a comment, Jonathan?
Yeah, I think separable. I would go for separable, particularly given the Maple code that's been provided.
Yeah, so this is also something important. Maple was given. I haven't looked really too closely at the Maple, which is mostly because I know when it has to come in. But let's grab it now. So we have this Maple code here, which is telling us how to do particular integrals. Now, actually, this could also help you with the linear one as well. It could help you find an integrating factor. But I think I want to do this one as separable. So you might want to mute your mic, Jonathan. Right, which is separable. It is first order linear. You might want to try that one out, but here, when you work through the details, separable feels faster. So how do we apply the separable technique? Well, we separate the variables. Now, some people have different ways of doing this. I am going to write down 1 over p dp and a minus 0.2 over 0.3 plus 7.7 e to the minus t dt. But knowing the lecturers for this course, this sort of thing should never be written down. We don't really have any way to make sense of this. But luckily, I'm just going to write down integral signs and no one's going to really know. So we have these two integrals having to be equal. And I think this is quite nice because the left-hand side is just a log. So this implies that we have the log. Now, if I'm cautious, it is the log of the absolute value of p, but p is measuring an amount of pollution. It's a positive number. So this is one case where you're fully justified by ignoring it. In the second case, well, this is where I should get the maple code. So we have this code here, and you should see, well, there's a number of things that this code does. One, it just gives me an integral for this expression here. Well, actually, not quite. What it does is it gives me an integral for this expression here, but it also just reminds me that these two things are the same. This expression you could integrate by hand. It's not too hard to spot the integral, but it is given in the code right here. So I'm just going to apply it based on the numbers I see. So actually, I'm going to sort of work backwards. I've applied it, and I've applied it where c is equal to minus 0.2, where a is equal to 0.3, and where b is equal to 7.7. I really need to do this step first, otherwise I can't get the numbers in correctly. So according to the code, so actually I might just say this is from the maple code. Okay, so just carefully plugging this in, we get a minus 0.2, that's the c, over a, which is 0.3, times the log, and it's just the log of the denominator. So that's the log of 0.3 plus 7.7 e to the minus t. And integrals are only done up to constants. Oops. So I need more space. It's up to a plus c. Oh, okay, I shouldn't choose c because c was already used, plus d. Okay, so we should try and apply our initial condition now. Or we can try and clean it up first.
Let's say, Josh, does that say a e to the t plus b rather than a times b e to the minus t?
Oh yes, you are right. Sorry, I was looking at the wrong expression. Thank you for that. Right, okay, so what do we get? What do we get? We got a, which was 0.3, yep. E to the t, and b was 7.7. So yes, this one, need to slow down, be careful, make sure you're doing the right thing. Okay, now you could solve for d at this point but it actually doesn't look like it's too hard to get an expression for P first. So I think we should probably clean it up a bit, then apply the initial condition. So taking logs. Oh, sorry, no, taking exponentials. Cancel out the logs. So you're going to get, well, you have this minus 0.2 over 0.3. That's the same as minus 2 over 3. And log laws say I can pull this up inside the log. So I will get P is equal to the exponential of D times the exponential of the log of this expression of 0.3 e to the t plus 7.7, all of that to the power of minus 2/3. Now, the exponential of d is just a constant, so I'm going to rewrite that as another constant. I guess let's just keep going up in the alphabet. E by the way, we can still hear you, Jonathan. Thanks. So we have that. Now is a good time to apply the initial condition. So the initial condition was that the initial amount of pollution was 4 tons. So that's P of naught equals 4. So this was just P of T. So using the fact that we know at initially at 0 months, 4 tons, we get, well, what do we get? We get 4 is, so I better hurry up. So 4 is equal to E times, well, if you plug in T equals 0, you get 0.3 plus 7.7, that is an 8 to the minus 2, which is E times, oops, which is E times, well, this is quite nice, it's really just 2 to the minus 2, it is E 1 over 4. So that means E has to be 16 to make a quarter of that equal to 4. All right. So what do we have? So hence we have P of naught is equal to 16 times this expression, which was 0.3 e to the t,
P of
7.
P of t?
Oh, yes. Thank you. To the minus 2/3. Let's double check that. Yep. All right. So the last question, part C, is actually just to use this to answer a question. So find out when the pollution drops down to 1 ton. Now, if you look at this, you can actually see, oh, thanks. You can actually see that this is decreasing, but it's a very simple thing. Just have to solve when does this expression equal 1. So we need to solve P of t equal to 1, which is equivalent to 1 is equal to 16 times this. Which is fairly nice because I can, let's see, so what's that equivalent to? So I need 0.3 e to the t plus 7.7 has to be equal to 1 over 16 to the power of minus 3 halves. So this is at least 1 over 4 to the minus 3. So that's 4 cubed. 4 cubed is 64. Wait, sorry. Yeah, it's to the power of 6. That's 64. So we just need this expression to be equal to 64. So i.e., we need that 0.3 e to the t is equal to 64 minus 7.7. So 64 minus 7 would be 57. So 57 minus 0.7 is 56.3. So that is equivalent to e to the t is equal to, I'm going to just move the decimal point to get 563 over 3, or in other words, t is the log of 563 over 3. I hope that is correct. So if I've done this correctly, then the answer, once I plug it into a calculator, should be around about 5.234. So that's around about 5 months, 5.25 months. So you could try and convert this into something involving days, but let's just say, so finish off by saying, hence the pollution will drop to 1 ton at about 5.23 months. And you could convert that into months and days, which probably is what I would really do in a real situation.
I think in a real exam, though, it'd be fine to write 5.23 months.
Yeah.
But if you're reporting to someone who's paying you to give them this answer, then
Yeah, they probably want to be able to understand your answer as quickly as possible. So
yeah.
Right, so I think that was all the questions. Now, so you said we will share this, but I might try and just clean up some of these parts before we share it out, especially correct those typos.
Okay, I think we're done. Any last questions before we go? If not, good luck for the exam.
Yep. And yeah, there will be there'll be the algebra stream soon, in about an hour and a half.
Yep. And recording of this will be available, and I'll also post this notebook once it's all synced and tidied up. Okay. Well, thanks for coming and asking questions.
VOD. I'm not sure how long is VOD video?
I don't know what that.
Video on demand, I see. Okay.
Well, I don't know. You have to email the IT people at Blackboard Collaborate in the US. I think it takes it's a 2.5 hour video, so it takes a lot to encode, but maybe an hour or something like that.
Okay. Well, we can stop the recording now.
Oh yes, we'll stop the recording.